Hello everyone and welcome to another episode of Solving Advent of Code in Rust and try to learn Rust in between. I'm Roberto and we have
Luciano, hello.
thank you everybody for following along. If you never did Advent of Code, Advent of Code is a challenge that is published around the Christmas period every year. We are working toward last year one. There are 24 challenges that you can find them on adventofcode.com. We are publishing all our code on GitHub. We also have a YouTube channel where we publish all the recording, and you can find the link in the description of this Twitch channel. Last time we did exercise 2021 because we already had the working pull request for those. This time we'll do exercise 2022. We have already part 1 and 2 in Python and part 1 in Rust. So we have to read the README and work on explaining part 1 and doing, if we have time, because this exercise is a little bit tough, we have to do part 2. So do we want to start with the README?
Yes, do you want me to show the README or you want to do it?
If you have it ready.
Then I'll do it. Let me switch scene and we should be able to see my README. Let's see. Yes. Okay, so always remember that Advent of Code is kind of a story where we need to save Christmas and we are kind of going through different adventures to kind of use code to help us overcome certain difficulties, right? So let's see what's the adventure today. So in this particular year, 2021, everything happens on the ocean. It's like underwater. We lost a key in the ocean and we'll need to go with a submarine and find it. So everything happens inside this submarine. So operating at these extreme ocean depths has overloaded the submarine reactor. It needs to be rebooted. The reactor core is made up of a large three-dimensional grid made up entirely of cubes. One cube per integer, three-dimensional coordinate x, y, and z. Each cube can be either or on off. At the start of the reboot process, they are all off. Could it be an old model of reactor you have seen before? And there is a link in a previous challenge, I think day 17, but doesn't matter. To reboot the reactor, you just need to set all the cubes to either on or off by following a list of reboot steps, which is your puzzle input. Each step specifies a cuboid, which is a set of all the cubes that have coordinates which fall in a range that is defined by x, y, and z. And whether to turn all the cubes in that cuboid on or off. Let's see an example because that will make it clear. So these are like instructions. We have one per line and our input will be much bigger. And basically it means turn on all the cubes where the x coordinates go from 10 to 12, the y coordinates go from 10 to 12, the z coordinates go from 10 to 12, and so on. So if we kind of try to decompose the first step, that basically imagine that you are starting with a 3D space where everything is empty. As soon as you see in this instruction, that it means that you need to understand how many cubes are being created. You can imagine those as like 3D pixels. And basically at that point, if we look at this thing, we have 27 3D pixels and we need to turn all of them on because this is
There is a name for 3D pixel and these voxels.
Yes. Oh, we should have called this voxels. Okay, so this is pretty much how it looks like, right? You are turning all of them on just to execute instruction 1. Then you execute instruction 2, and it tells you again, set all of them on, the ones that match this kind of set of coordinates, and there are other additional 19 cubes or voxel points. And then there is a third step where this time saying off. So when you find off, you actually have to turn all of them off. Of course, if they are on, if they are not there, it doesn't matter. So in this particular case, if you try to apply all the points in this space, there are 8 cubes that needs to be turned off. And
so
then
on.
the last step, you have 39 and so on. So here we have a larger example where you have all these different points, and you can see that some coordinates are actually very big. Like here we have 54,000 and so on. So you might end up having a lot of points. So the last two steps are fully outside the initialization procedure area. All other steps are fully within it. After executing this step in the initialization procedure region, 590,000 and so on cubes are on. Execute the reboot step. Afterward, considering only cubes in the region minus 50-50, minus 50-50, minus 50-50 in the 3 different axes. How many cubes are on? And here we have our solution. So if all of that is not clear, feel free to ask questions in the chat and we are going to try to answer them. If not, we are just going to go through the code on Roberto's screen, right?
Yeah, I think it's worth reading part 2 also, because I think it's another one of those exercises where part 2 is just, okay, do the same, but remove the constraint from part 1.
Yeah, so basically there is just a larger example here, and it's saying, here is just removing the constraint that you need to be in that specific region, minus 50-50, minus 50-50, minus 50-50 in the 3 different axes. So you can imagine, just by looking at how big are these numbers, that here you might end up with billions or trillions of points if you're trying to represent every single pixel univocally. So there needs to be like a smarter way of representing regions in a 3D space that doesn't require you to initialize every single individual voxel or 3D pixel or
and then you must be able to turn regions on and regions off while you go through our input.
And you can see here that the number is just much bigger in terms of answer.
Yeah. Show also our input just to get an idea of.
Let's have a quick look at the input.
Big it is.
Exercise 22 input. There you go. Is more than 100 lines. It's very long. 420 lines.
So we need to find a way to do this in as smart as possible way to not use all the memory in the universe and to not use all the CPU time of the universe. So
okay.
So if you want to switch to I will explain the Python solutions and then we can jump on the Rust one. So this first one is just a visualization of our input, my input, that is slightly different from Luciano's one, but just to get an idea, those are huge coordinates, so 68,000 and so on. So if you see, they go from minus 100,000 to 100,000 in all the 3 axes, and this is more or less in the shape of a sphere, more or less. The blue, I think is like a dark blue-green color are the ones that are on. The red one are the ones that must be turned off. And if we take a look, we see that some of them obviously overlap. They cut through each other. This blue one is there. And if we go inside this cube from inside, we can see that my browser is not keeping up. And we can see that there is a lot of strange shapes around, but still we can't. This one is cut in the middle. We can't keep in memory every sync voxel of this because they will be really too many of them. So this is our input visualized. I made various solutions in Python. Let's explain the one that is the winning one, I want to say. That is the first idea that I had was we have cubes.
Can I mention something very quickly before you explain this one? Maybe just to recap what would be a naive solution, which we are going to see Rust, because in Rust I only implemented a naive solution so far. So just give you a little bit of preview, because I think it makes what you're going to explain a little bit easier to grasp. But you can imagine that we basically have ranges of coordinates. If we initialize a space where literally like we have 3D pixels, so we could set all these 3D pixels in an hash map, where in this hash map we only have coordinates for one point, so the 3 coordinates. That solution will probably work well enough for the constraints of part 1, because you're basically, what you're doing, you read every single instruction, you understand which pixels are part of that instruction, and then you add or remove those pixels from the hash set, and then at the end you just count how many items do you have in the hash set, and that's it.
And this is how I solved the part 1, by the way. So I set a grid that is a set of coordinates. For every line of my input, I set f to 4 or 3, based if he's on or off. So if he's off, f would be 4. If he's on, f would be 3. Then I use this number to parse the line. I'm just doing a trick. And I have coordinates. Then here we do that.
Just one point, Roberto, do you mind?
Oh, yeah, sure.
Enough? Yeah, I think that's better. Thank you.
Cool. Then this is the 6 lines that do the limitation of stay between minus 50 and 50.
Mm-hmm.
Then these are the 3 nested fors to go through all the voxels of every instruction. If it is on, I add to the set. If it is off, I discard, that is a remove, from the set. In the end, I just tell the length of the set, and we have the solution for part 1.
Mm-hmm.
And this is the naive approach. Obviously, with part 2, the naive approach is not working. So to solve part 2, what was in the end the idea? The idea is to take all the input, get an idea of the number of times Z will be splitted. I mean, if we have a cuboid area that starts from 0 to 100, and then we have to remove something that goes from minus 50 to 50, it means that we have to be able to remember that between 0 and 50 there will be something, and between 50 and 100 there will be something else. So basically we are reducing the space from a linear space to a not linear space, where every step by 1 is instead a step of 20, 30, or 17 coordinates. But I'm doing this only for the z-axis. Doing this only for the z-axis give out a total of around 850, more or less, divisions of the space. Even if we have huge numbers, there are only 850 planes. Then
like ranges, right?
Yeah, ranges. Then inside those planes, what I did, I kept remembering these rectangular shapes with 2 coordinates. So when I have x and y, I just take care of x and y, and I don't have to turn on all the points between the 2 x and y, but I just have to remember the 2 points. All that area will be turned on for me. When I have an instruction to turn off an area, I have to do difference between rectangles. This is this difference visualized. So here we can see all the possible stuff that can happen. Can happen that this rectangle to remove is inside the rectangle to keep. Can be that the rectangle to remove is top right, or it is in between left, in between up, bottom left, in between right, and so on. Then there is the case where a rectangle is overlapping horizontally another rectangle. The case a rectangle is overlapping vertically another rectangle. This one empty is the case a rectangle is the same or bigger of the rectangle that is positive, so the negative one is the same or bigger. This is the case that the negative rectangle is not touching at all the positive rectangle, so the positive rectangle stay what it was.
Mm-hmm.
Doing this logic by plane made me this pure Python solution that we can see together in a moment, that is taking 5 seconds to compute this huge number. But this is pure Python, then there is a Gitted version. To go a little bit more specific to what it does, this is the description of the algorithm itself. This one is keeping a list of the 850 planes I was talking about. Is parsing the input twice. The first pass on top of the input is to get an idea of how many Z planes we have, and to create a set of them and a dictionary that tell me, look, plane that starts at coordinate 8000 is 3000 units thick. Then another one that starts at that point to 12,000, sorry, can be 12 units thick, and so on. Just keep the thickness of all the planes. I need the WZ, that is weight in Z. My idea was like a weight of the plane itself. Then the real algorithm is this one. I create a dictionary of planes. For all the lines, I parse them. I get an idea if it is on or off. Then, for all the planes that are touched by the instructions that I'm going to execute, if the plane is not in the dictionary, I put it in as an empty list. This could have been done with a default dict, but I was lazy. Then this plane is equal to this plane where I subtract my current, at this point, rectangle, because I'm just caring about X and Y, because Z is handled here.
Mm-hmm.
And I take all the square that I have, and I remove my current rectangle that I have in the current line of the input. Then, if it was an off instruction, I'm done. I turned off the area. Cool. If it was an on instruction, and my f is equal to 3 if it is on, if my f is 3, so I have to add instead of remove, I add to the list just the whole rectangle as turned on. So the whole area will be turned on. Doing this over and over again for all the lines of our input, I will have a bunch of planes with a bunch of squares. For every plane, I compute the area of all the squares, and then I multiply the area of all the squares by the thickness of the Z plane, and in the end we have our solution. Here I'm using this function that is the heart of this algorithm, that is making differences between rectangles and a rectangle. This is a list of rectangles, and this is a single rectangle. This diff is implemented here, so it takes, I call them squares. They are not squares, they are rectangles, but when I was thinking about it, it was hard, so I kept the name squares, but those in reality are rectangles. So the subtracting rectangle is x3, x4, and y3 and y4. Then I cut the squares by the top left coordinate, so by those two coordinates. Then again, I cut all the squares that come out of that cut by the bottom right coordinates, that will be this one. Then I keep only the squares that are not inside the subtraction square. So first step, I split the squares. I don't remove them, I just split them. Then with this line, I remove all the squares that are inside the subtraction rectangles. So at that point, I will not have those anymore. Here I'm doing something for optimization. That is, I sort the squares, and I collapse the squares that are touching. For example, if we go back to the picture from here, if I'm not going to do that, if I'm not going to reabsorb touching rectangles, this image will not come out with 4 rectangles, but this image will come out with 8 rectangles, because there will be a line here, another line here, another line here, and another line here. So those will be 8 rectangles, not 4. And even here, I would have another line here, so there will be 3 rectangles, not 2 rectangles. Even here and here, I would have another 2 lines here and here, so there would have been 2 more. But the number of rectangles in this algorithm make the algorithm slow. So
yeah, because every time you will have to iterate on more rectangles.
Yeah, I have to iterate on all the rectangles every time I do a cut. So every time I do a cut, I iterate on top of all of them. So the more they are, the slower it is. So here I'm doing this logic of putting back together rectangles that touch. We could skip this for the first part in Rust, because this is an optimization. It's not mandatory. It's working even without this. It's just slower. Then what is the cut? The cut is taking taking a list of of rectangles, and it's say, given a point, it say if the point is in X inside the rectangle, append 2 rectangles splitted on X. So you have this rectangle, you have to split by this vertical line, and you split it in 2. Then you redo the same operation for point Y, and you split the rectangle by horizontal lines. So every time you split a single rectangle, you can come up with 4 rectangles. I mean, you can, because it's not always happening, because the point can be outside, the point can be only cutting in vertical and not in horizontal, and so on. But in the end, we do this for all the squares in this SQ, that is a list of rectangles, for all the rectangles in this list of rectangles, and we go on like this. And at that point, we have the cut. And then there is the inside function that is quite simple. It means a rectangle is inside of another rectangle if the coordinates are inside. Yeah, so touching, because the equal is for touching, or inside. So those are all the primitives that we need to resolve part 2, and in pure Python is taking 5 seconds. Last time we said that with Numba we can make stuff faster. Just to give you an idea, the algorithm is exactly the same, but with the decorator for Numba, and it goes down from 5 seconds to 0.5 seconds. Then there is another optimization again that we can apply, and is cutting the squares only if they touch. And by touch, there is the definition of when a rectangle is touching another rectangle that are again coordinates. With this additional optimization, we can cut down the time in half again and going to 0.24. This is not a lot of code to write, but we have to be very, we have to be types and stuff like that. One question could be, from your point of view, why you are not doing this instead of rectangles that cut rectangles with cubes that cut cubes? Yes, I tried to do that. Here is working. This is the code. The problem with this approach, in my opinion, is that is more code, more prone to error. Look at this definition of touch. Is complicated. More prone to error, harder to write, harder to understand, and on top of everything is slower. For some reason, is slower. And this is the number of cubes at the end of all the cut and stitch together. And this is again the same answer as the other part too. I prepared a graph to show you about all of this, but sadly my browser is not keeping up showing it to you because plotting almost 7,000 cubes in JavaScript in Colab, the browser is suicidal. It's not able to. I have the code here, but it's taking 20 minutes to run, and the browser is JavaScript wants to die, and it's not good.
Let's blame JavaScript.
Yeah, let's blame. No, but obviously doing 3D graphics with a lot of points inside a browser, inside Colab, inside all this game of Chinese boxes, obviously is a little bit painful for the machine, and my machine is not a huge one. In any case, the algorithm is this. The primitive that we need is being able to parse the input. Nice. Being able to do differences between a list of rectangles and a rectangle. To do the difference, we need to be able to cut a list of rectangles by a point, and we have to be able to tell if a rectangle is inside another rectangle. It's not a lot of code in the end. And we need to be able to slice all our universe in thick section of Z.
Mm-hmm. Yeah, you're using Z as an index, basically, right?
Yeah. I keep stuff simple and to reason in 2-dimension instead of 3. Then I also did the 3-dimensional reasoning, but it was slower. I also tried for this one the GPU approach to all of this, but I got really, really lost in all the passing of cubes around. So 0.24 second is a big achievement for me.
Yeah, I'm curious to see what can we get in Rust.
Probably faster. We can implement the same algorithm and it will be faster for sure. But yeah, it's normal. I mean. So, do you have part 1 for Rust, you said before?
Yes, let's have a quick
And this
look.
implemented it more or less in the same way you were saying?
I think so, for like the naive version that we described at the very beginning.
Yeah.
So basically, let's look at the
Do you want to share your screen?
Yes, I am sharing it, I think. You should be able to see it.
A moment, for some reason I can see your screen. Just a second.
Maybe it's just lagging. I can't see it in the preview.
Okay, now it's working. Sorry. No, my machine was lagging because when I show you the graphs, my machine started to cry.
to suffer.
Yeah.
Okay, so basically part 1, as we said, we try to represent everything as a hash set where we store every single individual 3D pixel. So we will add and remove those 3D pixels as we go through the data, and then at the end we just count how many of them did we get. So this is literally our space, right? So every item is literally a tuple with 3 values, which are the X, Y, and Z coordinates of every point. Then we have commands, which is parsing the input. So it's basically taking the input, every single line is doing a map. We will see that we have a command struct and an easy way to parse a command, a line string into a command. And then we're also doing a filter where we check with this function incube max50 if it's part of that initialization area that we care about for exercise part 1. So at the end of the day, this is just giving us commands that make sense to run for part 1, a vector of commands. Actually, an iterator, because we are not even materializing this view. We are just specifying the iterator operations. Then what we do, we say for every command in this list, well, in this, let's call it generator here, for lack of better words, or iterator. For every command in this iterator, what do we do? So we will have ranges for the 3 coordinates. And in the command, we will have property x range, y range, and z range. And they are all tuples. So 0 and 1 will be the lower boundary and the height boundary of every coordinate. So basically this will give us a list of x's, a list of y points, a list of z point, and then basically what we want to do is, if we are on, we need to insert x, y, and z. If we are off, we need to remove x, y, and z. Does that make sense?
Yeah, and then in line 82, you return the size of this hash set.
Then if we want to see a little bit more of how I implemented command, so command is just a struct where on is a Boolean. If it's true, it means that we want to add. If it's false, it means we want to remove. And then X range, it's an I sides, Y range, Z range, and so on. Then what do we have? A command as this function incube, which basically tells me if the current command is inside a region, a 3D region. So you are just specifying the maximum. This is really bespoke for the kind of problem we have, where I'm assuming it's like a cube. It's a proper cube. So any center is 0 and it goes to plus that value and minus that value. Minus. So basically it's just saying, if you give me 50, I'm going to go from 0 to 50, but also from 0 to minus 50 in every coordinate, in every axis. And that is just telling you, okay, the current command, is it in that area, in that region, 3D region? Yeah. And this will give you just a true or false. And then finally here is all the parsing logic. So basically what we do actually here, because it's just one character, Lippy was complaining that you don't need to create a string. So here what is exactly, we split on space first, and then we check on the left side we have if it's on or off, on the right side we have all the ranges. So it's on only if the left side is literally strictly equal to the on string. Then we need to split all the ranges by comma, and then at that point we get the 3 ranges, and then I could have probably, this is literally a very crude copy paste, I could have probably generalize this, but basically what I'm doing is for every range I'm just splitting on the dot dot, and then just taking the 2 values out of it. And then at the end I have all the values that I need to create on, and then you can see here that every one of these instructions gives me a tuple, X range, I size, Y range, I size, so I can just fill in my command. Let's see if by the way, I tried this naive approach for part 2 without even thinking that it's gonna make my memory explode, and it did explode. So this is not gonna work for part 2, and we need to do something smarter like Roberto did. Oh, we have Tommaso in the chat. Hello, Tommaso. How are you today? So let's see if this runs. Should run. Running one test. And it did finish. This is not running in... This is running in debug mode, so it's quite slow. But it's still taking like reasonable time. 2 seconds and 22. We will run the benchmarks later. So now, what do we want to change to implement part 2?
Okay, we still need the list of commands, so you have all the parsing and you can retrieve the list of commands, and that's fine.
So all of this stuff is pretty much there. We have it. Part 2.
Yeah, for part 2, we parse the input, same as before. We have the commands. We have to cycle twice on this if we want to do exactly how I did in Python. There is any problems looping twice on top of that commands? No, it's not going to.
There is, but we... I guess we can do 2 things. Actually, I'm not sure. Let's see. I think there will be problems unless we do it through reference. Let's see if we do for command in commands, right? And just do this. And then we do for command in command. I think it's gonna complain, but let's see.
Because the second one is already.
Oh, input needs to be the right one. Yeah, the second one it was moved, I think, when we did this for loop. And it consumed the iterator. So what we could do is either initialize this again, or we materialize all of that into a vector. I have a feeling that reparsing all of that again
Is faster.
is probably faster, but we can test this assumption.
Oh, well, for now, let's reparse so we can create another let commands chew or let's commands, yeah,
So
and
Maso
redo the loop.
is shouting at us in the chat.
To do a reference in the first loop.
Yes. So to
Let's
do
try.
this.
In the second one, we don't care. In the second one, we can destroy the object itself.
But I think if this will work, but the second time you try to do this, it will be empty.
It will be empty. Can you rewind an iterator?
Ooh, good question. It probably depends on the type of iterator.
Well, Luciano, you know what? Let's go with two declarations or cloning the iterator.
Yeah, we could actually do like commands to equal commands.clone. Right?
Then we can leave.
At this point, I think you can do this.
Yeah, we leave to future us optimization to avoid that ugly clone, but for now.
But this clone shouldn't be too bad because at this point it's only keeping references, right? Because the input doesn't get cloned.
Okay,
and then we only create one line at the time. So the amount of memory that we allocate at any given point should be efficient, I suppose. Yeah, I just don't know if it's just faster to allocate all the entire vector and use it twice rather than recreating it step by step 2 times. We can test it later.
Yeah, but let's go with this for now.
By the way, can you repeat why do we need to go through it twice? Because maybe I missed that.
Because the first time that we go through it, we just care about Z. And we try to understand how many layers of Z there are and how thick they are.
Okay. So let's
that probably there is a way to do that at the same point when parsing, but it would be more complicated. So we need two variables. One is a Nash set of Z's. So a Nash set of E-sides, you created them?
Needs to be...
No, just one number. A Nash set of numbers.
Okay.
Do you need round brackets or is just one number? Okay. That obviously must be empty at the start. Default is not something that you can do.
You can do that, yeah. I think
I-size has a default of 0.
Does that work? Oh, yeah, I'm doing something.
Too many equals. Why inferred that boolean? Oh, okay, who cares? Okay, and then we need a map of E-size to some other number that is the thickness of that layer.
Okay.
Probably those can become only one variable at the end, but let's try.
What if we do a Nash map where I-size is the key and the thickness is the value? Would that be the same?
And to create the hash map, we need that set because we need to sort that set. So we need a sorted version of that.
Okay, then let's go Z thickness, I guess. Yeah. And this is a Nash set of I-size.
It's a Nash map. Is a Nash map of I-size to I-size. Not to U-size because the thickness is...
because it's always positive.
Yeah, it's always positive, the thickness. The thickness can't be negative. So now the algorithm to compute the thickness is the following one. We have to take all our Z ranges that is a set and sort them.
Okay, so let's fill Z ranges first.
That's
Should we?
Yes, the first step is filling the ranges. You're right.
So what we want to do
for
is
command in commands, but you already have the line in line 96.
I'm faster typing it than copy pasting.
Perfect.
Okay, then what do? We say Z ranges dot
add
or insert.
Please add, insert, append. What else?
And we want to do.
We need to add the command Z0 because it's a tuple, right?
Do we consider Z0?
Mm-hmm.
Because in command we have Z range, right? So this is what we want.
Z range dot 0.
Dot 0, but we want to do.
And then we also have to add dot 1 plus 1, because remember that the voxels, if it is a voxel from 5 to 5, is still one voxel that must count 1, because like you did in your 4 in part 1, they were all inclusive. Remember,
so you are only putting ticks in the space right now. You are not really filling anything, right? You are just putting like little flags in the Z space.
Yeah. Okay. These start here and then here.
In reality, here we know that there is space between this value and all this value, right?
Yeah. But at the end of this, when we have a set of Z, we know that if we have 50 and we have 57, we will never cut in between.
Mm-hmm. Do we need to do if command on?
No, we need to do that always.
Okay, so this is just ranges where something happens, basically.
Yeah, where something will happen in the second iteration. Okay.
Okay.
And the set is to avoid duplications, obviously. Now, let's populate the Z thickness. That we need a sorted version of Z ranges, and we need to go with window of 2. Remember the windows of 2? I don't know if you can sort a Nash set. Doesn't make a lot of sense.
Interesting.
I don't think it makes sense to sort a Nash set. At least in Python, you can't sort set. You have to create a vector of values and then sort the vector. Or I don't know if there is a primitive to do that in Rust.
Let's see, in the ranges dot. Let's see.
Dot iter dot sort. No, collect.
No, I think
you collect a vector and then you sort the vector.
Probably that's what we need to do. So we need to do mute, and then we need to do Z range sorted dot sort.
Yeah.
I guess.
Yeah. Now to compute the
collect. Wait a second.
Into iter, we need into iter to get the ownership of those numbers.
I don't think so, because they are I sides. So let's see, what's the problem?
Yeah, try into iter because it's complaining about borrowing. Into. And now it's up.
Okay, fair enough.
Oh my god, I started to understand what into iter means.
And Ashmap needs to be imported.
Also, Tommaso was saying the same on the chat. So,
thank you, Tommaso.
So now go with a window of 2 on top of this vector.
Cannot borrow. Oh yeah, of course this needs to be mutable as well if we are adding stuff. Cool. Now, what did you say? Sorry, Roberto?
Now that we have our vector of sizes, go on top of it with windows of size 2. You remember the usual, I want the first one and the second one, then the second one and the third one, then the third one and the fourth one, and so on. We did these other times, if I remember correctly.
Yeah, so we need to do a zip. I think this is how we did it.
We didn't use the crate that is doing that game.
You can also install Ether tools if you think it's better.
I'm just
let's do with Ether tools because
what is the most Rustonic
probably the one
rusty way of doing this. Okay, I was saying Pythonic. Sorry, guys. I don't want to offend any Rust user. And also, I think Rustonic is not. Sort, I hope, is ascending.
We can use.
And if it's not, we will have all negative thickness, and our number will be a mess.
I don't remember how you use it.
But searching the code, we used this before. So if you search window or something.
Yeah, I remember that you can do something like that. You can do Z ranges sorted windows. That's the one, and sides 2. And that should give us an iterator. So basically we can say for A and B, right?
A and B, yeah.
This, and that A and B should be, why it's unknown?
Unknown, perfect. Right.
Okay.
Try to search. Return an iterator over contiguous. If you do Command Shift F and you search for window, you don't find anything. Tuple window. Okay. But without a size. Is inferring the size from the number of parameters you want to.
Is that the way it works? Okay, let's review this example. So what were we import? Oh, I need to import Ether tools. Okay.
Where the star is not
gonna make a difference. So here what we were doing is tuple windows filter count.
Yeah, we were just counting the number of ascending. This was the exercise with the number of ascending steps. So we were turning through if the A was greater than B. But yes, the syntax is that one. Have you installed it with Cargo, the crate?
Oh, okay. Tommaso is giving us the solution. Sorry for ignoring you in the chat.
Into iter, because a vector is not an iterator, right?
Pretty much. So we need to do dot iter.
We need this. We need the sorted version later. Let me think.
Okay, now we have A and B. Yeah.
No, we need the set later. We destroyed the set with that into iter.
I think we did.
Because we need that later, but when we need it, we will find a way. Okay. Now, what do we have to add to our hash map? That we have to declare that mutable before this loop, because the one in line 105 must be declared before. Yeah, because otherwise we can't add stuff to it. And as mutable, I suppose.
And this is going to be mutable, yes.
So this is the thickness of A. So we have to add
thickness. We need to get.
No, we have to set.
If it exists.
No,
well,
it's going to not exist, and we will always add new ones, because coming from a set is impossible that we will loop on the same key twice.
So
the
we
key
insert
is A, and the value is B minus A. The thickness is B minus A. Yeah.
Oh, I see now. Okay, so that's why we sorted. So we put all the flags, then we sort them, and then we see, okay, this is going from A to B, so it's long as B minus A. Yeah, fair enough.
And then again and again and again. Now he's complaining about 1000 stuff. That is always positive. We know that. You can declare it as usize if you want, but we know that that will always be positive because we are sorted in ascending way.
Yeah, so what's the easiest way of doing this?
Put it between round brackets as usize, and then it will go in panic if we are not. If it is negative, it will panic, but the sort is assuring us that it will never be negative.
Mm-hmm.
And if it is, we have an error, and we will fix it. Right?
Okay. Yes. So at this point, we created Z ranges. We filled Z thickness with all the starting points associated to their sides, right?
Yeah. All the possible starting point with their sides, exactly. And this will be needed when we compute the final area of the turned on voxels. Now, second loop is on top of the input and is doing the logic of diff and not diff of stuff. Do you want to start writing the code here and then going down to the primitive, or do you want to start with the primitives and covering them with the tests?
We could create a library.
Okay, let's create a library for differences between rectangles.
Okay, so and we define also
the tests there.
Let's call it rectangle, right? Because everything we want to do there has to deal with rectangles.
Yes, that will be a function to do difference between a vector of rectangles or an iterator of rectangles. We can say a vector just to be.
Okay, so here we can already define a struct for a rectangle or not?
We can define a struct for a rectangle that will be 4 integers, 4 sides.
So it will be basically the 2 points.
The 2 points.
Corner and bottom corner, right?
Yeah.
So what do we call it? X0, right sides.
We also need a primitive for a point. So at this point, we can create the point structure and then declare the rectangle as 2 points.
Point.
Good point is X and Y. X is size and Y is size. Then a rectangle is they are 0.1 and 0.0.
So P1
or P2, yeah, P1, P2.
Let's call it P0 because I like it.
Okay. And those are of type point. Cool.
And
then we will deal a lot with vectors of points. So I don't know if you want to create an alias for a vector of rectangles. Sorry. Do you want to create type alias for rectangles? Is a vector of rectangle. Typos to me. At this point, we can start with the first function to define, that is the differences between rectangles and a rectangle.
Okay.
That is
retarding. Let's implement it as a free function. So
it's taking rectangles. Is taking another rectangle to subtract. So
and it returns what?
It returns rectangles.
A new one.
Yeah.
Or does it need to be mutating the original one?
In my Python solution, I was creating new ones.
Okay, let's do it the same, and then if we can optimize later, we'll do it.
Yeah, there are 3 or 4 points of optimization in all of this, and we will not do them now, for later. So here, then we need this. Leave this function.
I like
there
that
for now.
Tommaso is suggesting the rectangle list is probably more obvious what's the difference, I guess.
Yeah, with the S is a little bit.
It might be easy to miss one from the
Yeah.
other. Yeah.
Now, let's define the signature of all the functions, then we start implementing them. Another function that we need, to do. Another function that we need is cat.
Oh, everything needs to be public.
Oh yeah, for now, let's make everything public. First, probably the point will be private, but yeah, we can make it private later. Now, cat, the rectangle list doesn't need to be declared as public because it's an alias.
I don't think it matters, because it's an alias.
Yeah. Cat, the cat is private for sure, but you can start declaring it as public. But cat will be.
Yeah, there is a thing called pub in crate, I think, or something like that, that allows us to say this is public only for this crate, so it's not really public.
Now, a rectangle probably is needed also side, but let's make everything public. We can
crate, we mean the entire exercise 22.
The entire exercise is a crate. Okay, so
let's do it this way. I think that should work. So cat.
We can cat takes rectangle list, takes a point, of type point, and return a rectangles list. So when you have a rectangle, you split by a point, you can come out with 4 rectangles. And when the input is multiple rectangles, you have to do this for all the rectangles in the rectangle list. And then you need also the third and last function that is inside, that takes 2 rectangles and tells you a boolean.
Is inside.
Takes rectangle 1, rectangle 2, so 2 rectangles. I don't know if you want to call rectangle 0 and rectangle 1. I don't.
Yeah, let's be consistent.
Or A and B.
Or
I mean,
0. Come on.
Yeah, they take 2 of them, and then it's just returning a boolean that tell if this is true if R0 is inside R1. If you want to leave a comment as first line of the inside function. Returns true when R0 is inside of R1. Yeah, exactly. Okay, let's start implementing from diff. Do you want to start from there, or do you want to start from?
Yeah, sounds good.
Okay. So now we need to take a rectangles, sorry, and cut rectangles by the first point of rectangle. So we have to call cut.
Thomas is suggesting us to put 3 comments, which I believe means.
What is? Is a doc string.
Exactly.
Okay, it's like a doc string in Python. Cool. But why is complaining about your doc string now?
I have no idea what this means.
But well, let's go on. Don't care.
Oh, because I'm not using this function, so it's like why I'm documenting it or something like that.
Okay, cool. Give us a second. So back to us in diff. The first time that we have to say is cut all the squares in rectangles by the first point in rectangle. So
okay, so for
no, you don't need to for. You just have to cut, because cut is already taking a rectangle list. Right. So you pass rectangles, and you pass rectangle P0.
I already see problems with reference here, but let's see.
We will address them.
Okay, then
When what comes out of this is a rectangle list.
Mm-hmm. So we
I'd
can
say
say
Tommaso
that,
say that the comment goes before the function, not as first line of the function. If I
that
understood
was why he
correctly,
was complaining. Yeah, fair enough. Good point.
if I am understanding correctly, but okay.
Yes, no, I think he's right, and it's not complaining anymore.
Now we have to take what comes out of the first cut, and we have to cut it by P1. So now we have to cut R, comma, rectangle P1. So another cut R, comma, rectangle P1. At that point, we have cut the
Now it's
all the
gonna complain or not? Oh, it doesn't complain. Why it doesn't complain? I'm surprised. Maybe because we are not yet returning.
Yeah, okay, that's it will complain in the future. Now we have to keep all from R the R from line 15, from that R exactly. We have to keep so filter and
Okay.
keep all the squares that are not inside rectangle. Retain is to keep stuff.
Yes,
Okay.
so the opposite of what you just said. We need to retain the ones.
Okay, we have to retain all the one not inside S2.
The
Not
ones
inside, how is called your rectangle?
is
Rectangle.
inside.
No, we have to discard the one that are inside, and we have to retain the one that are not inside. Okay, inside takes the R, that is your
Current one, yeah.
the current one, comma
Rectangle.
rectangle.
Right?
Yes, exactly. Because if we go, is R inside of R1? R1 is our rectangle. So yeah, if it is inside, we have to discard it. If so, we have to retain if it's not inside. Cool. Okay, makes sense.
Mm-hmm.
Okay, now we are in this way. We are keeping the one that are not inside. Cool. And at this point, we can return R.
Okay, now we start to think about references here because it's already complaining here, right? And the first obvious thing is like here you don't need to take ownership, right?
Yeah,
Oh,
because we are just
Giuseppe Verdi is following us. Amazing follow. As somebody from Catania, I feel
originale, so original,
yeah.
not the fake one.
Thank you, Giuseppe. How are you doing today? I hope you have new songs for us.
Yeah, a new national anthem, if you have time. Why is complaining about line
because
60?
We
line
moved the
16.
rectangle when we started to do this, I think. Oh
You
no, because it
can't
was
pass by
setting a
reference.
reference. Wait. Yes, no, this is good. Now, what's going on here? Why doesn't like this one?
You are
Borrow
shadowing.
partially moved. Okay, does not implement the copy trait. So every time we do, where did we move it? Let me see where move
Line
occurred.
14, no 15.
Value partially moved in line 15, and then in line 16 we are using it. So because here we sent.
Okay, but can't we send a reference to P1 instead in the cut? Can't we take as second parameter a reference?
Yes, I think so. And here we can do this. And this. Is that gonna be good enough? I think so. Cool. So
Now,
this is
let's we can implement or inside or cut. Choose one.
so Giuseppe Verdi is telling us in Italian, so I'm gonna translate. An Italian, actually two Italians, that do Rust are a mandatory follow. Thank you for that. Are you doing Rust as well?
We are trying. If you do, tell us something because we are trying.
If you see us doing stupid things, let us know.
So many of them. And this is the gesture for so many. Now let's implement inside. It's easy. It's just a fast function. Returning a
Yes.
Boolean.
So inside is basically doing what?
Okay, inside means that the x of R0, the x of the first point of R0, must be greater or equal. So R0 dot P0 dot x. Yes. That is the x of the first, must be greater or equal of
R1 P.
R1 P0 x, exactly.
Yes.
And then the R0 P0 y must be greater or equal of R1 P0 y.
And
R0 P1x must be less or equal, the other way around, of R1 P1x
X.
and R0 P1y must be less or equal to R1 P1 y. Sorry.
Cool.
Okay.
It did not like it in multiple lines. Okay, sorry, Rust formatter.
And now it's not used. No, it is used. It's not true that it's not used. It's used in line 16.
It's never used it, I guess, because this one is never used in a main.
But well, we have to use that in part 2. So okay, take it easy. We can write test on top of this, to be honest, before using it.
Yeah, I guess the easy way to make it stop complaining, if you do pub mod, then it kind of means that from the top level of the crate you are exporting.
You are exporting this guy.
So I think now it's going to stop complaining.
But I don't care if he's complaining. Let it complain. Complain is good.
It's still complaining. Cool.
Where is Copilot when you need it, Tommaso says.
Exactly. Is it disabled? Oh, I have disabled it. Let's re-enable it. It would have done this one on its own, probably.
Wrong. Cool.
Okay, cool. Let's go. So cat, what do we do with cat?
Cat needs to create an empty rectangle list to return, so a new one that will start mutable and empty.
And we can result and mutable.
Yeah, but they probably.
I love the no, when you return, it's already inferring the type.
Yeah, it's inferring the type from the return. Yeah. Also, there you can do the default again, or
you could do the default. I think I'm not too sure. Let's see. Oh, is it the other way around?
Don't you need to call default?
No, you need to call. You're right. And it's the other way around. Cool. Okay, it did work.
Okay, now for all you have to loop on top of rectangles. So for all the rectangle in rectangles, okay, because Copilot was saying something.
Let's see what it's trying to do. Does that match what you want to do? I have no idea.
I don't know what the fuck he's doing.
No, I don't think. No, I don't think.
No, he's pushing a result, and I think the only line that makes sense is pushing result, but you can rewrite it. The only line that makes sense is result push, but okay, this is just a way simpler if than all of this. The if is just. Can you concatenate conditions in Rust, or you have to put 2 of them in AND? I mean, A less than B less than C.
No, I think you need to put them in.
Okay, cool.
I think.
Okay. So now, if rectangle.p0 dot x less
Okay,
than
I am
point
already less than.
less than point. Okay, I like this, but I don't like it in reality. And then, yeah, now you have to say that point x point x is less than rp1x.
Okay, so
Copilot was
if the
suggesting,
point is in between
yeah, is in
the
between
extreme.
of the rectangle we are on. If we are in between, open something, square brackets. Okay, we have an S also, but okay, rectangle push. Let me see if this makes sense.
So Maz is saying this is why you probably disabled Copilot. Yes.
Yeah, no, but the code was the code that was suggesting was
Not
good.
hearing
Was
you
not
anymore.
everything.
Sorry. Okay, you are back.
Sorry, where am I?
No, I was not hearing you anymore. Now I can. Sorry about that.
Can you hear me? Okay. Now the code
Yes.
that was suggesting was good, but was not everything. Was just a part of what we need to do. But was suggesting something. Yeah,
There,
keep it,
right?
keep everything.
Mm-hmm.
So this is between 0, 0 and x. Perfect. This is perfect. You have to do this again. So copy and paste all of this. So there are two push because we are cutting. Okay. So our rectangles become two rectangles. So you push this, then copy and paste this result push, and we have to change the coordinates a moment. Now we have to go from the first x is point x.
Point x, yes.
Yeah, that one is point x. And the line 40 is, that is fine. Line 40 is rp1x. Yeah, rp1x. Cool. And in the else of the if that starts in line 23.
So we go here.
Not 23, that was 22. You are doing an else on top of a 4. I need the else on top of the if. So going line 44. Yes. Yeah, off by one curly brackets. Here you have to push R. Yeah, exactly. You have to. That's good. Push R. Now with borrowing here we can. I don't know, because we're creating a new object. Probably we can take ownership of R or not.
Type annotation is needed if you use default. So if you use vec, it's not needed.
It's not inferring the type.
With default, no. Can you hear the ice cream music?
Yeah, we can hear that. But probably will be here next. So okay, and now we cut it by vertical slice by x. Now we have to cut by the point y, because we did the cut by point x. We need to do the same cutting by point y. So we have to loop on top of our current result
before returning it, right?
Probably we need to create a new one to,
because we cannot modify a result as we loop through it.
No, right? We can't modify result while we go through it, so we need to create a new one, a new real result.
So let me do one thing, which unfortunately we have to do. We can do derive, clone, and debug, just in case we want to print something. Not the root, derive, yes. Cool. And now we should be able to do something like for or in result.clone.
No, but we need to add to an empty rectangle list, not to the same.
To an empty rectangle list. Why?
Now we have a list of rectangles. We are cutting all of them by x. Then we have to take this list of rectangle, return a new list of rectangle cutted by y.
Right, so we don't need to clone.
No, we need just a new empty one, a new empty result that will be the real final result. And the type, I think, will be already inferred by partial result. Cool.
Now we will probably infer by the push.
Yeah, if you push, no, you have to push to partial result, because now you are pushing to result in line 26.
Yeah, right.
So if you push to partial result, probably is inferring. Yeah, you see, you already inferred that is a vector of
Cool. And now result is, let's mute
immutable
result.
default, yeah, vector, and it will infer the output. Now, for all the rectangles in partial result, I think you can copy and paste the body of the other 4, and we just have to change the coordinate system.
We need to push in the other one, basically.
Yeah, we need to push in result and not in partial result. Okay.
And the coordinate
we
system
have
needs to change, right?
the if also needs to change.
Because we need to look into y.
Yeah, we have to do the
Right.
same, but with y. Yeah. If point y is in between of the rectangle y's. Cool. What is Copilot, please? Yeah, to answer Tommaso, yes, this is why we disabled Copilot, because he's thinking too much. The point here is, sorry, my brain is warming up. Okay, line 61. Going line 61.
So line, all of this
That
is
is
correct.
fine. Yeah.
Oh, here we need to switch them, right?
RP1X on the top. RP1X, and on the bottom point Y. Yeah. If by switch you were meaning this, yes.
Yeah, because now we are looking like vertically, right?
Yeah. And in 67, you have to say RP0X, and then you have to say point Y, because we are going vertical slices. Okay. We have done this. Done. We return result. We did the cut. We did the insert, and in theory, diff is working. Do we want to write a test for diff? Yeah,
I
I want
so.
to write a test for diff.
So mod tests, and let's see if I can remember for once. Copilot.
Copy and paste. Copilot is not helping. He's always chatting.
It is.
Okay.
It is okay. And now we can do test. We can do fn. What do we want to test first?
Diff. Let's test the diff. If diff works, all the other are working.
Okay, so what can we diff? Oh my god.
We'll keep something because okay, too much.
Okay, too much. Cool.
Well, you're right. Let's start testing a cut. And let's see if he's suggesting something that makes a little bit more sense. No, he's not suggesting.
On Copilot, you can do it. It was thinking, and now let's see what's the result.
So okay, try to keep everything, because I'm super cool.
Let me try to understand. So it's creating a list of rectangles where the first one goes from 0, 0 to 2, 2.
Yeah.
And the other one is going from 1, 1 to 3. So
3.
They do overlap. And
no, but this is to cut by a point. So then he's creating a point.
Oh yeah,
it's cutting.
Okay.
It's cutting the two rectangles by a point in 1, 1. And it's coming out with a rectangle.
They shouldn't be 2, right? Because 1, 1 is in between the first rectangle, so it's create 4 rectangles.
Yeah, in theory, it's creating 4 from them and not touching the other one.
This one is not going to be cutted because it's just at the edge.
Yeah.
So we should have 5 in the end, right?
Yeah, we should have 5, not 2.
4. This one stays as
Stay the same. But well, you can keep the code. We can just change that 2 to a 5, and
let's see if our assumption is correct first. So this should fail, saying Must
the
implement
equality.
why?
If the point is not implementing equality, because there
Oh,
is an
because
assert
it's
equal.
trying to do an assert equal. Okay,
But
fair enough.
remove though, I don't care. Well, if we we will need to assert on top of points at one point. Yeah, and probably also for rectangles we need to assert it.
Okay, now let's run this, and it should fail now, saying that we were expecting 5 and we got 2, right? Perfect.
Yeah.
Left is 5 and we got 2. So let's fix this. Now all the points are what we expect.
This is the first rectangle is from 0, 0 to 1, 1. Makes sense. I don't know if it will be the first, to be honest. But one of the rectangles will be that one. I just don't know if it will be the one with index 0. Try to run
Fair
it.
enough. Yeah, and I was thinking maybe it's better to write where we assert over rectangles and not points. Let's see. Yeah, this failed because it was not 0, 1. It was not 1, 1, but 0, 1.
Yeah, because we don't know in which order they got returned.
So let's just do something else. Let's just do let expected rectangles, right? And this is a vec of, we expect 5 of them, right? So the first one is a rectangle.
Copy,
you know what?
Keep it. You want to print it? You can't debug. You can't debug result, and then we can copy and paste from there.
Wait, x0, x, y0, x1, y1, and all of them are I sides.
Yeah, even the last one.
Then I want to return this. Yes, thank you, Copilot. And now here what we can do is easily just say rectangle new and pass all the coordinates that we expect, right?
Yeah, I don't know the order, but let's try to expect.
No, for now, I just want to list all of them, and then we can do a for loop with contains.
Ah, okay. Cool. Okay, let's go. Copy that line for to have 5 of them.
The line.
Accept the Copilot suggestion.
Oh, and
copy the line
5
times because we have 5 of them. One will be 0, 0, 1, 1. One will be 1, 1, 2, 2. One will be 0, 0, 1, 0. No, wait. No, moment. Where is it? It will be 1, 0. My file.
I don't know if we can draw it somehow because it will be something like this. Let's see if we can do a nice ASCII art. Look at that.
Oh my God.
Thank you, Copilot. Cool. No. Now you need to split again. Yeah, that.
Oh God. Nice.
No, come on, split.
Almost there. Copilot for ASCII art.
Okay, so here is 0, 0. So this will be
1, 0. And
this
1, 1. 2, 0.
Yeah. And here we have, what is this? This is gonna be
0, 1.
1, 0.
No, 0, 0, 1. 0, 1.
0, 1, yeah. And
one in the center is 1, 1. And that one is 2, 1. 2, 1. 0, 2.
Now this is 0, 2. This one is 1, 2.
Yeah, and then we have 2, 2.
Right, so let me make this smaller. So now what we have is a rectangle that is 0, 0, 1, 0,
1,
no, 0,
1.
0, 1, 1.
0, 0, 1, 1. Okay, then we have 1, 0, 2, 1.
1, 0, 2, 1, 1, 0.
1.
Let's do them in order. 1, 0, 2, 1. Then we have this one, which is 0, 1, 1, 2.
1, 2.
0, 1, 1, 2.
Then we have 1, 1, 2, 2.
1, 1, 2, 2.
And then we have the 1, 1, 3, 3 that was not touched.
The one from before, which is 1, 1, 3, 3. Yes.
That must not be touched. So
Right in the middle. Right, okay, so now what we want to do is for...
we are using a vector. Could we use an hash set task, Tommaso? Yes, probably. We could have used a set. This is an optimization that later we can do, but when are we...
For the test?
No, probably for also the solution, but later when we'll optimize to put...
Oh, just to compare them, right?
Yeah, but one optimization is to put the rectangles back together. To do that, you must sort the cutted rectangles. If you have a set, you can sort a set. Instead, you can sort a vector.
Okay, but here what I'm trying to do is just this.
Yeah, just assert that they are there. Is a vector of 5, it would not take a lot of time to assert all of that. So is this green? Because it's already
nice.
7:30 and we have the tools to solve this. It will take a little bit of time to solve this, the cut. Do you want to do that now, or we send this to next episode?
No, I would say let's wrap up here for today, and
we have working tests in our libraries, and next time we will use the diff from these libraries to do all the job having solution for part 2. Makes sense?
It does, yeah.
Perfect. So let's wrap up. You can find the recording on YouTube. The link is on Twitch in the About section. If you're watching this on YouTube, we do live streaming on Twitch every Monday, 5 p.m. UTC, 6 p.m. Dublin time. Make sure to check the Twitch link in the YouTube description. Give us a follow, click the bell so you can get notified, and the usual stuff. Feel free to leave us comment and open PRs. The repository of code is on GitHub. Everyone is well accepted. We are trying to learn Rust, so don't expect our solution to be the most idiomatic ones, even if they are getting better, to be honest. We are doing the same stuff over and over again. We are learning. We are not so bad.
We almost did 50 exercises at this point, so it's...
Oh yeah, so I think it's something.
It's a good amount of Rust, to be doing in 2 years.
If you know better ways of doing stuff, please tell us, leave comments on YouTube, open pull requests, everything is well accepted. Thank you for the suggesting in the chat. And are we going to raid somebody, Luciano?
Yes, we are going to be raiding Coding Garden, who always does amazing live projects, mostly in JavaScript, so I hope you're going to have fun.
Probably can speed up Colab and all the 3D graphs that we showed before that are crashing my poor machine.
Hopefully.
Okay, thank you. Bye, and see you next time.
Bye, everyone.
Bye.